Okay, there is a pattern to systematic error. So both of these things imply that it could conceivably be corrected for. Okay? So, because both these things are true, systematic error could be corrected. If you knew about it, or if you figured it out, for example, and you might be able to detect it. So if you could figure it out, like a great example here is when we're using the triple beam balances, which we'll be using, and they're not zeroed. Maybe you figure out at the end of the experiment, you're all done, and you let the thing settle, and you realize it's not coming to zero when there's nothing on the pan. Systematic error. You could correct for that, though. You could figure out what you have to do to make it come to zero, and then you could correct your data, potentially. So systematic error could be corrected. All right? Now, what will it do? So the effect of systematic error is here. The effect of systematic error is to shift the mean. You all know what I'm talking about by the mean, right? Shift the mean from the true value. Now this true value I mentioned last time, although I don't think I used those words. This is the true quantity, the true measurement, which, by the way, we can never know. All right? I'm sorry if that makes you uncomfortable, but it's true. We can never know for sure the true value. We can start to be more and more certain about it, right? As time goes on and we replicate and replicate and replicate, the more replications we have, we can narrow in on that thing. But we will never know it exactly. But there is one. At least that's our assumption. And it is assumption, actually. So we're off. It's going to cause us to be off from the true value. All right? But does generally not increase scatter. And what I mean by that is deviations, okay? Deviations of the data points from the mean generally doesn't cause that kind of scatterness, right? So, in other words, it decreases accuracy no real effect, and you might argue with me on this one, but no effect on precision. All right, so I just used two new terms there, accuracy and precision. Let me illustrate. This is the classic illustration of accuracy versus precision. Let's take two targets, and I'm shooting at the targets. I know the word shooting is not supposed to be said, but I'm shooting a bow, okay? I'm shooting a bow and arrow at these targets. And where am I going to hit? So in one case, that's where my shots fall, okay? The other case, they fall there, like that, okay? Now here's my question. Which shooter, let's say these are two different shooters, all right? Two different shooters shooting at this. Which shooter is more accurate? Colleen. One on the right, why do you say that? Okay, good. And then, by default, I guess the other one is more precise, okay? More precise, less accurate. So we're going to say more precise, less accurate. And this one is more accurate, less precise. And this reveals a very kind of nice, neat definition of these two terms. Accuracy. Accuracy is nearness to the true value. Precision is nearness of the points to each other. And nearness of the points to each other, we could call this repeatability. Repeatability would be a synonym for precision. Accuracy is nearness to the true value. Precision is nearness to the points to each other. Okay, now here's the question, and we'll move on to random error. Systematic error is most closely related to which? Accuracy or precision? Martin. Why do you say that? Okay, yeah, good. Is most related to accuracy. In other words, I could say this. Look, I could write and say, okay, here's my difference. This is my difference between the true value, which is my target, and where my data are, right? The average of my data. This difference, this deviation, if you will, is due to systematic error. If I'm shooting, then what's happening is I'm doing the same thing wrong every time. You know, maybe I'm pulling up to the right every time for some reason because I flinch a certain way. Or maybe it's my sights need to be adjusted. So if I was shooting a gun, I would adjust my sights. On the second one, that's not the case. Okay? I appear to be aimed right at the center, but something's causing scatter. The first one is actually better. I would, if I was a shooter, I would rather see the first target, because that actually means I'm a darn good shooter. I just need to correct something. I need to tweak the system a little bit. All right? The second one is actually worse, because whatever it is I'm doing different every time. Right? So maybe it's a kind of shakiness. See what I'm saying? And that brings us to the second kind of error, which is random error. Random error is more insidious. It can't be removed as easily, if at all. Okay? Random error is much harder to remove. It's almost like it's natural. In fact, to some degree it is. This is also another synonym for this, or a synonym for random error is uncertainty in measurement. So this is what we did yesterday. This is the kind of error we were detecting after we took out what we suspected to be some systematic error. So we removed some outliers because we thought that might be due to systematic error. Let's get them out of here. There was actual errors in procedure. Somebody read the thing wrong. Okay? Got rid of those. What we're left with is just this kind of natural variation. Uncertainty in measurement. Causes random fluctuations. Let me say seemingly. We don't really know what we mean by random anyway, so causes seemingly random, unpredictable fluctuations. Seemingly random, unpredictable fluctuations. Deviations from the expected value, or of the points from each other. Picture it like this. I mean, the target analogy is great because you can picture somebody shooting and they're just kind of shaking. Maybe they drank too much coffee. And so they're just shaking while they're shooting and the thing's just scattering all over the place. That's random error. Now, I suppose you kind of blur the lines a little bit. You could say, well, that's systematic. Get the caffeine out of his system and shoot better. I don't know. But the idea is it's random. It's not a regular systematic kind of thing that you can easily correct for. Systematic error, you might be able to transform the data to correct it. You might be able to subtract a value from every number or multiply every number by the same factor or something like that in order to correct for it. If you had to. This, no, not so easy. What could you do to reduce this? Because there is something. I said it's more difficult to remove, but you can actually reduce it. How could you reduce it? Let me just say, could be reduced by. Anyone? Think about my analogy with the shooting. Jesse.
Like using a ruler or like something that precisely measures the.
So change your instrument. Okay. Change your instrument. And we saw this yesterday. Change your instrument. So in other words, use a 10 milliliter cylinder instead of a 100. It's pretty simple. Instead of using this, use this one. If you can, if your volumes are small enough and you can, you're going to get a lot more precision with this. Notice I didn't say accuracy. A lot more precision. We're talking about precision here, not accuracy. Yes?
But is random error just like misreading? What are you saying right now?
It's not. Okay, well, that's good. Let's talk about that. Right.
What does that do? It's still going to have the same amount of whatever, right? Or it's just in a different
That's true.
class?
That's true. You'd have the same true value, presumably. If I could like transfer all of this, every last drop, into that, I'd have exactly the same volume. So what's going on here? I guess we should let's take a little side trip here and just clarify this more. Where does this even come from, right? This source of error. So let's look at a measuring instrument. And I'm going to make a graduated cylinder here because that's what we were using yesterday. So here's my graduated cylinder. And here is my meniscus. And I'm going to say that this is 50 milliliters right here. Right? Now, how would you read the volume on this? If this is 50 and this is 55 right here. Anybody want to give me a reading? Remember, you read the bottom of the meniscus. Thomas. 51.5. Anybody? Anything different? I might say it's a little higher than half. I might say, in fact, I'll just throw a plus or minus point. Yeah, let's be a little generous, 0.2. Because I'm not sure that's 55 and a half. That could be 55.6, even 55.7. Do you believe me? Okay. This is random error. Okay, random error, uncertainty in measurement. That is random error, uncertainty in measurement. Where does it come from? It comes from estimation. Okay? At least when you're measuring something, the source of the random error is due to the estimation process. Okay? So in this case, the nature of measurement includes estimation. It always does. See, because there are not an infinite number of lines on this cylinder. right? There's not an infinite number of subdivisions. There would have to be in order for me to get an exact reading. There'd have to be an infinite number of subdivisions, and I'd have to be able to see those infinite number of subdivisions and to match them up with the bottom of that meniscus. But because there's not, I have to estimate one digit. And by the way, the rule is you're allowed to estimate one digit. It's meaningless to go beyond this. Hopefully that's clear. I wouldn't want to write 51.52 because I don't even know the 0.5, so why guess on the 2? Follow me? So I don't write 51.52. You can guess on one, not guess, but estimate one digit. This estimation process is always present, but the instrument changes the precision of the estimation. How? Let's look at a 10 milliliter cylinder. Well, in a 10 milliliter cylinder, the lines are closer together. In this case, instead of each line being a milliliter apart, they're a tenth of a milliliter apart. So this would be 50, and this would be 50. Well, let's actually do this. Okay, now see, here's the thing. The lines are all important because you can tell if the meniscus is above or below a line. Right? And so you know the line for sure. The line represents a value that you know for sure. So in this case, let's say my meniscus now is, I can't do the same volume, sorry. I have to continue this up. The same amount of liquid might look like this. In this vessel. All right? And so what I would write for my volume is 51 point something like that. So what I'm doing is it's like I'm narrowing in on it because I'm making more lines. I'm making the lines more closely subdivided. And I'm getting greater precision out of it. Right? It all has to do with the lines. What graduations do the lines represent? What differences? Are they a milliliter apart? If they're a milliliter apart, then the most you're going to do is estimate between milliliters, which means to the 10th. Okay? If they're a tenth of a milliliter apart, now you can estimate between the tenths and maybe get down to 100th of a milliliter in your precision. To get smaller than that, which you could, to measure volumes more precisely than that, you might need to use a syringe. Like there are some real precise syringes where you might get 100th of a milliliter divisions. Actually, we have some pipettes that can do that, that have actual lines 100th of a milliliter apart. Then you can estimate between the line and get 1,000th in your measurement. So, this does not mean that one of these is more accurate than the other. You don't know which is more accurate. That depends on how well they made these things and whether they calibrated them correctly. Okay? But this one is definitely more precise, simply because of the estimation process. Every time I look at that, I might get a different estimation. I might see it a little bit differently. Every person who looks at it might give a different estimation, just like you all did when we were going around the room. I made a concerted effort when I filled these up to try to make sure the meniscus fell between lines and not on a line. Because if it falls really close to a line, I found in the past that the students tend to lock on that line with their volume, and so it becomes very reproducible. But if it's between the lines, then everybody's got to guess. Is that half? Is it 4/10? Is it 6/10? 7/10? So the instrument is important. Change your instrument. Get a more precise instrument. And we can do that. costs more money. So it's not, when I say it's harder, one of the things I mean by harder to remove, you're going to have to buy a better instrument in a lot of cases. It costs more money to make something that's that precise than this. Same thing with balances. More precise balances cost more money. So the heart of uncertainty of measurement is in the estimation process, although there are other errors, which I will talk about next, because the other thing you can do, well, first of all, any questions on this part right here? Estimation. I would bet that some of you don't believe me when I say that in every measurement there is an estimation involved. Am I right about that? Some of you don't believe me. Can somebody give me an example of a measurement in which there would not be an estimation involved? Let me say this. Let's say I'm using a yardstick or a meter stick. And I think one of the reasons this is difficult is because a lot of times we just don't try to measure precisely, and so we don't see ourselves as doing any kind of estimation. But you are. Even if I round this to the nearest tenth of a centimeter, which I can read right off of here, there's actually a line every tenth of a centimeter, every millimeter. That's what I'm doing. I'm rounding it. If I say this is 46.3 centimeters long, I'm not claiming it's exactly 46.3. Exactly. 46.30000000000. That's not what I'm saying. I'm rounding it to that. I'm saying it's close enough. That's an estimation. The fact that I went to 46.3 instead of 46.4 was an estimation. And if I try to get more precise and I try to estimate to the 100th, that's going to be an estimation. You can't get away from that. Because I don't have infinite divisions on this thing, and even if I did, I wouldn't be able to resolve them with my eyes. Okay? Now, some of you might say, go digital. That'll solve the problem. Was anybody thinking that? But here's the problem with that. Now, right away, you should be a little bit uncomfortable with that. Because the concept that simply having a digital electronic instrument would remove this problem seems too good to be true. It is. When I have a balance, like the ones you used in bio probably, and I drop something on it, it says 51.5 grams, does that mean 51.50000000000? No. The instrument's doing the rounding for you. It's like whatever it's closest to, it's going to bump it up to that decimal. You follow me? It's got to be that way. It's not infinitely precise. Otherwise, it's like if you've got a balance that only goes to the tenth of a gram, you'd be saying that everything you could possibly weigh in the universe, the mass always increases by tenths of a gram. Isn't that amazing? Well, it's not true, right? We have balances that'll go to 4 decimal places back there. In that back room. They're called analytical balances. 1/10,000th of a gram they will measure. $1,500 per balance. That's why I say random error is harder to remove. Those balances that give you a tenth of a gram, 150, 200 bucks a piece. You want to get a 10,000th of a gram, 1,500 is cheap. So removing this error is difficult. But there is one other way, and this is what you guys are going to do this year. That is practice. All right? I think the analogy with the gun or with the bow is a great analogy, because that one who was scattered all around, but he was around the target. What he needs to do is practice. And the reason here is that there are other sources of random error, not just the estimation. There's just little random fluctuations that are coming in from small changes in the way I'm doing things. The angle at which I'm viewing it, right? If I'm not being careful. I'm just being a little sloppy. Now that's not systematic because it's not regular. All right? They're little sources of random error. Maybe my hand is shaking when I'm using the balance. Maybe there's wind kind of randomly blowing through the room, which will happen in here. So there's other sources that we can practice, can reduce. Other sources of random error. So you can literally get better at weighing things on a balance. You can learn to detect when there's fluctuations that there shouldn't be. You can get better at making sure you read in the same way every time, making sure I get on the level of that meniscus, making sure I'm reading the same part of the meniscus every time. All that sort of stuff comes into play. And you get better at it. One of the things about science is that it's really a human endeavor, and a lot of science is actually skill that's passed on from one scientist to another. That's particularly true in the laboratory. It's probably true in theoretical science as well, but it's particularly true in the laboratory. These are hands-on skills that some people never really get good at it. Some people are good at it right away. Just being able to be precise and careful and stuff like that. And in your measurement. It can make an enormous difference. I mean, this kind of thing, like having this down, could make the difference between proving and disproving something. Follow me? It could make the difference between missing a discovery and not missing the discovery. Because what random error does is random error, so this is kind of the effect now of random error. Random error generates noise. Noise, not physical noise, but it generates noise in the data that clouds things. It obscures it. It's like a smudge. Like a smudge. Cloudiness. It obscures the true result. So it's really, I mean, so does systematic error in a sense, but this one is more of like a fuzziness that it adds to the data. There's actually a third way that we can deal with random error, and probably the most important: increased replications. Can help with random error. Doing increased replications can help this. So we generally want to do more replications rather than fewer. Generally what will happen is with random fluctuations, the more replications you do, the more your average will move toward the true value. The larger the population sample you take, the more the average will be like the true value. And that makes sense. If I take only 3 measurements, there's a better chance that 2 of them were way off or something, right? But if I take a huge number, then chances are they're not all way off. Okay? So the more you take, the more measurements you take, the more you're going to approach the true value. Let me give you an example. I'm flipping a coin. It's supposed to be 50-50 heads, tails, right? Does that mean if I flip it 5 times, if I flip it 6 times, I'm going to get 3 heads, 3 tails? No. Does that mean if I flip it 100 times, I'm going to get 50 heads, 50 tails? If I flip it 1,000 times, will I get 500 heads, 500 tails? If I flip it 1,000,000 times, will I get 500,000 heads, 500,000 tails? I'm getting close now. What I'm saying is the more times I flip it, the more it's going to be inexorably drawn toward that true 50-50 value. Theoretically, if I flipped it an infinite number of times, it would be exactly 50% heads and exactly 50% tails. Follow me? The more times I flip it, the more times it will replicate that 50-50. Not every time, obviously. You know, it's not like I can predict whether it be heads or tails in any particular instance. Yes?
But random error can still get it, even that too.
That's true, yeah.
Depending on one specific side.
Right, yeah. Yeah, so that's why even if you had 1 million, you know, it might be 501,000 and 499,000. Yeah. So it's still going to sneak in. But the point is, the more you do, the more replication you do, the better off you are. What it has the effect of kind of washing out. It's almost like by mass, what do you call it? By brute force or something, you're kind of pushing out the random error just by more and more and more replications. So increase replications, and in general, you're going to see this on the first lab. The more times you can repeat the experiment, the better. And that makes sense, right? Because if you're making some random error, then the more times you repeat it, the more likely you are to have some good measurements, too. Okay. So this is a lot of stuff, I know. Any questions on this? This is terminology that we've been going over here. I know you probably have questions. I know that you're all going to want to listen to this again. That's why I recorded it. Because it's been exciting. And I know you want to repeat this experience. So, it is important though. You know, I don't know why I just get excited about this stuff. I know you can tell. To me, the whole concept of measurement is just really cool. And I haven't always thought that. I hated math when I was in high school. I guess I liked measurement. I went to Ellis Tech. I was architectural drafting in that shop there. So I guess I always liked measurement and being precise and stuff like that, even though I didn't know it. I didn't realize it at the time. But the reason it's so cool is because here's the essence of measurement. You're trying to match one thing to another in the world, right? So that we can kind of see patterns, or we can, whatever we're trying to do. I mean, think of all the uses measurement has, really. We don't even think about it, but without it, I don't know, it'd be hard to do anything. But this act of trying to match things reveals, it gets at this whole question of knowledge and what we can know and how we can know it and all that kind of stuff. So to me, measurement is a very philosophical enterprise. That's why I think it's interesting. It's kind of like it gets to this whole question of what's called epistemology, the philosophy of knowledge. What we can know. All right. There aren't any questions, or you guys are just A, bored stiff, B, confused to such a degree that you don't know what to ask, C, tired? Okay, good. All right. Well, let's get a little more concrete here. We started out showing you these measurements. I had 636055, so I got 2.63, 2.60, 2.55. Let's get a little more concrete. By the way, that discussion is going to come in very handy on the error section of your lab reports, because I'm going to want you to discuss the major sources of error and what their influence might have been in your experiment. Now, some of you might notice a glaring omission from that. Nowhere up there did I write, you might make a mistake as being a source of error. And yet, that is the most commonly cited source of error on student lab reports in my experience. No. My question when you write that is, did you make a mistake? And if so, why didn't you correct it? And if you didn't make a mistake, or if you don't know that you make a mistake, then why write it? Okay? I want to hear about real sources of error that you really think happened. Okay? Now, let me just temper that a little bit. If you dropped half your sample on the floor and we didn't have any more sample, then definitely put that in there. We made a mistake. We dropped the sample. Okay? I'm saying I don't want this kind of ambiguous, we might have made a mistake in our calculations. Hey, you might have, did you? Look at them. Look at your calculation. Did you make a mistake? You should be able to tell that. You shouldn't just have to say, oh, this might have happened. Yeah. A gravity wave might have passed through and thrown our balances off. Right? Some wizard might have stopped time and come in and switched our samples on the balance while we weren't looking. Yeah, it could have happened, I suppose. No, I want realistic things that you really think happened. So how do we quantify? So right now we're talking about quantifying error. Quantifying error. First of all, let's quantify systematic error. Let's quantify systematic. Now this is different from the true value, so obviously to do this we need a true value. Problem with that, we don't know it, right? So what we usually use is we usually just look at the difference between, you know that symbol, B/W, between our average and some accepted value. In other words, you look it up in a book or something like that, and you say, what should this be? Now let's just say this is supposed to be quartz, or we think this might be quartz. So, for example, quartz has a density of 2.65 grams per cubic centimeter. So I just looked this up maybe in a book like this. This is the Handbook of Chemistry and Physics, Pocket Edition. The normal book is much bigger than this, but this thing is just chock full of data. Everything you could want to know about, like all the different chemicals and stuff like that. So I look it up, and it's an accepted value. It says 2.65 grams per cubic centimeter. I have some systematic error, because what's my average here? So my average is 2.63 plus 2.60 plus 2.55 divided by 3. My average is 2.59. All right? 2.59. I'm just going, for now, I'm just going to the same number of decimal places. We'll deal with plus or minus in a minute. So my systematic error, we'll call this the percent error, because that's what it's called in your book, I think. This is an estimate of systematic error, is going to be equal to 2.65 minus 2.59 divided by 2.65 times 100. And you can see what I'm doing here. I'm just finding the difference between my average and the mean, the accepted value, and I'm expressing that as a percentage of the accepted value. So 2.65 minus 2.59 divided by 2.65. Oh no. No. 2.5. This gives me 2.26%. That's not bad. 2.26%. I'm calling that an estimate of systematic error. Not entirely true. That difference from the average could also be due to random error. Okay? But this is just the fact that I'm comparing it to a true value. I'm just showing you the kind of idea of systematic error, even though, like I said, the actual reason for this could be more random than systematic. Now, assessing random error. This is when I use the deviations. So we have two methods. We have the max deviation, and we have average deviation. Maximum deviation, taking the absolute value of these differences. Notice I'm subtracting the average, my average, from each of the data points. This is the deviation from my mean. Those are called the deviations. And they're absolute values. We don't want the plus or minus in front of them. So the max deviation, 0.04. And so I would write 2.59 plus or minus 0.04. Make sure you have the same number of decimal places in your number and your uncertainty. Same number of decimal places. And make sure there's only one non-zero digit in your uncertainty. Those are the two rules that I mentioned yesterday. Now the average deviation, what we would do is we take 0.04 plus 0.01 plus 0.04 over 3. I get 0.03. Notice that it's lower. As I mentioned yesterday, it's going to be lower. It's a more kind of conservative estimate of your error. You're saying that it's more restricted. That's the average. And so in this case, I would say 2.59 plus or minus 0.03. Now we can take Dr. Lewin's approach and we can use this data. We can say, do you have quartz or do you not have quartz? Do you have quartz? Do you not have quartz? What I'm saying here is that the density of my sample could have been as high as, so in other words, I'm saying it could go from 2.63 to 2.55. The true value for quartz is 2.65. This ain't quartz. Okay? Yes?
What if your measurements are wrong? It's size. Didn't know it was
Well, we're accounting for that kind of variation. Now, one thing we're not accounting for is systematic error. Okay, but in the absence of any understanding of systematic error, then all we got to go on is our variation in measurement, and we're going to have to conclude this isn't quartz. Unless, and I know some of you might have thought about this, why isn't there a plus or minus on the 2.65? Is that an exact number? No. But the fact is, when you look this up in a table, you are not likely to find a plus or minus on it, simply because they don't include them. So we'd have to, if you were really doing this for real, I would probably say, well, wait a minute, I'll bet you there's at least as much uncertainty on this as there was on my measurement. In which case, they could overlap. You follow me? They both have uncertainty, and so they can overlap. Plus, there's probably natural variation in quartz, depending on where it forms and how and stuff like that. So there's probably a lot of plus or minus. So that's how we use this. And here's what this can do, and this is why this is so exciting. It can take you from conclusions that say, I think we were right in your lab report, to conclusions that say, we can accept our hypothesis because the accepted value lies within the range of our uncertainty. Isn't that exciting? it actually gives you a reason. It gives you something to say in your conclusion that is a reason. It's like a justification that's based in the measurement process.